Welcome, everyone. I'm Shah. This is the Data Entrepreneurs. Very excited today because Jeremy is here and he's going to be talking about a real world LLM use case that he built for a client. We'll kind of get to see his tech stack and the problems that he ran into. And then if you guys have very specific hyper technical questions that he might not cover during the talk, you can always ask those in the Q&A session. So Jeremy and I have been LinkedIn friends, or just virtual friends, for the past year or so. We both studied physics. We were both thrown into the world of entrepreneurship and the machine learning and data science space. So I learned a lot from Jeremy, and I'm sure you guys will too. So with that, I'll just hand it over to you, Jeremy, and we can get into the talk.
Thank you, Sean. So very nice to be here. I hope you hear me well for the next 30 minutes, 40 minutes. I will lead the conversation, and I hope you will like the project I did for a previous client last year. So, gentle introduction about me. I'm Jeremy Arancio. I'm a machine learning engineer and MLOps engineer. I'm a French guy, so I hope my French accent will not bother you, or the opposite, you will like it. I'm living in Czech Republic right now, in Prague. Very beautiful city. I hope you're gonna visit it. I love it for 3 years now. Love ping pong, love playing chess. 1,400 ELO. Invite me on chess.com, a nomad data scientist. And that was for the gentle introduction. So now let's dive directly into the project. For a client, which is OpenFootFacts, I developed an ML feature and an LLM feature. I will talk about how I developed the features and how did we integrate it into the applications. So to talk about OpenFootFacts is a large open source database composed of over 3.5 million products. Food. He has currently 12,000 contributors worldwide. It's a multi-language company and a database. It has a mobile app and a web API. So what you can do with OpenFootFacts, because it's an open source project, you can either access any product via the web application. You can access the product through the mobile application, and you can also contribute to the OpenFootFacts database by scanning and taking pictures of products in the groceries and stuff like that. You can also add details. And so, like I mentioned, in 2024, so last year, I joined the core team as a freelancer. And with them, we developed a couple of machine learning features and LLMs to either improve the quality of the database or to ease the process, the contribution process. So let me walk you through the problem we solved using the LLM, because it came for that. So let me introduce you the ingredients spell check problem. So you are a consumer and you have your application and you have the OpenFootFacts application on it, and you want to scan some products to add those products to the OpenFootFacts database. So what you do is you take pictures and of the front of the package, the back of the package, and in the applications, if you ever used it, you are asked to take picture of the nutrients, logos, list of ingredients, and so on. With these pictures, what OpenFootFacts does is, let's say for the list of ingredients, it will extract via OCR the list of ingredients, so the text on the image. It will extract each ingredient from the text, and then it will perform some analysis on ingredients to then retrieve or store all the analysis and informations about a product. It could be the allergens, it could be the compositions, it could be like the percentage of I don't know, salt and stuff like that. So this is a process. But as you may know, if you work in a machine learning, the OCR is sometimes tricky. So, for instance, in this specific case, it happens that the list of ingredients are cut. If you look at lecithin, so you see my pointer. If you look at lecithin, the word was actually cut, and for the OCR, it doesn't matter. It would be like lecithin dash tin. You have also folded package and light reflections, which leads to unrecognized characters. and then you have products which have curvature. So you cannot really see the characters on the edge. How does it look like for OpenFoodFacts? So let's say you have this package with this list of ingredients in French, and the little folding on the package was not recognized by the OCR. And what you see is like an unrecognized ingredients, and OpenFacts monitor these unrecognized ingredients, and these ingredients will not be categorized as it is in the taxonomy. You wouldn't, let's say it's let me give you an example. Let's say it's the term cacahuète, which is an allergen, but because of the OCR, the cacahuète becomes cahuète, and cahuète is not recognized as an allergen or neither or as an ingredient. So for the analysis, the product is not considered as a product containing allergens. So it's, at the end of the day, it could be pretty bad for the database quality. So we needed to add, let's say, kind of a spell check to these OCR extractions. So this is what we did, and we implemented this feature between the OCR and the after the OCR extraction. So right away, I think like most of you can think about, this is text, we have LLMs, let's solve it using LLMs. This is a solved issue. We prompt GPT-4o and job done. And actually it is way more complex than it looks. So we need to step back and consider the feature as not as a machine learning problem, but as a industrial problem, like an enterprise problem. So first of all, we need to think, what is a typo? What is a OCR error? And which kind of error should be corrected or not? For instance, if you look at the percentage, so 121%, which is a wrong percentage passed by the OCR, it could be either 12.1% or 1.21%. So maybe we shouldn't try to correct percentage that are, maybe we shouldn't try to correct percentage at all, because maybe it would be better to let it as it is than implementing a wrong number, if you know what I mean. Same idea, 396 is actually a common OCR issue in the data, and it means 3%, because 96 corresponds for the OCR to percentage. But should we correct these numbers or not, this percentage or not? Another example, the data is a bit specific because OpenFacts and contributors, if they change the list of ingredients manually, they are asked to label each ingredients or each allergens. So for cacahuète, you're going to have the dash to indicate for the ingredient analysis that this is an allergen. So you have a lot of specificities that you need to handle. So the first thing we did for this project was building a guideline. So we called it the Spellcheck Guideline, and this is a guideline of 20 rules to guide any feature, which could be rule-based, ML, LLM, or any annotators, like doing the annotation campaign, to say you should correct this list of ingredients this way. So this guideline is the core of the spell check and will guide any solutions and annotations to make the project a success. Talking about annotations, before jumping into LLM, we need to be able to evaluate any kind of solution that could be LLMs, but that also could be rule-based or human correction. And we need to be able to evaluate any correction, any spell check. So for that, we're creating a custom benchmark of 320 lists of ingredients that are directly extracting from the OpenFacts database. We picked a list of ingredients containing 10 to 40% of unrecognized ingredients. Too low, there's no need to correct via the spell check. Too high, it would be like a noise, like I don't know, like the same words times 10 times. So it's just noise. So between 10 and 40%. And we manually corrected the list of ingredients using the tool called Argila. Argila is an NLP annotation tool. It's a very nice project now in the Hugging Face ecosystem. And for everything related to NLP tasks, it's super handy. And Argila will come often during these presentations and this project. So we have a benchmark with the original list of ingredients coming from the database and the reference, how we want it to be corrected. But how can we calculate some metrics based on this benchmark? And actually, the problem is a bit tricky. So let me show you. So let's say you have 3 sentences. You have the original sentences as it is in the OpenStack database containing typos. You have the reference. This is how you want the sentence or the text to be corrected. And you have the predictions from your, I don't know, human, machine learning model, rule-based method, LLM, anything. This is the prediction. But as you can see, like I can maybe show you. As you can see, like the reference means that this term is actually there, so it needs to be corrected. Cat doesn't have to change. This is a mistake, it has to change. And it missed a dot here, and we have a comma, so we need to change. This is a reference. This is how we wanted to modify our text. But if we look at the predictions, it seems that the prediction missed he added a word called the big. He correctly corrected is, and so on. So you can see that if you look word by word, you can say, okay, this one was correctly corrected and this one was not. So you can maybe calculate the number of correctly corrected words. So let's try that. So instead of having words, let's modify everything and having tokens instead. So to do that, it's kind of an embedding. Use the tick token library and using the BP algorithm. This is the same embedding system that is used in GPT. So I transform my text into tokens. And so now I can see like this token was changed in the reference, but didn't change in the prediction. And this wasn't supposed to change, but it changed. But actually the thing was actually just like it moved just because actually this one is a new word. So we need to have kind of an alignment between the original and reference and the original and predictions. So good for us in DNA or bioinformatics, there is an algorithm to align DNA sequences, and it's called Needleman-Wunsch, but you have different alignment algorithms, and it will allow you to align the sequence based on the common tokens. So for instance, these tokens were aligned, and now we can see that a new word was added. This one haven't changed. This was correctly fixed, and so on. So if you use 1 if the token changed and 0 if it didn't change, you can have this kind of stuff. And I don't know if you noticed, but now with these numbers, we can either calculate estimate the false negatives. So the spell check changed, but it wasn't supposed to change. A false positive, it wasn't supposed to change, but it changed. And a true positive, it was supposed to change and it changed. And so with this kind of algorithm, we are able to calculate the precision recall of our spell check for each word, which means we know that this spell check has a precision of, I don't know, 80%. It means that out of 100 corrections, 80% of corrections were right. And recall, 80% recall means out of 100 typos, we fixed 80 typos. So we have very good metrics, very common from machine learning, and we can estimate any solutions or evaluate any solution, like the LLMs. So we, using the same algorithm plus the benchmark, we evaluated different models, LLMs, and funny enough, GPT 3.5 was the best model over Gemini and even include Sony 3.5. There's some reasons to this. We have some hypotheses why GPT 3.5, but we can discuss it later if you want. So good, we have a model. Now we can go to production and deploy the model. But yes and no, actually. Because as you may know, GPT 3.5 now is actually, I don't even know if OpenAI is still maintaining it. And if it's still maintained, will it be in 6 months? This is the first point. The second point is, okay, but can we get better performance? I mean, we have data. Could we reach a better performance using maybe a custom solutions, a custom LLM? And we have also the issue of ownership. Like I mentioned in the first point, if OpenAI decide to turn off GPT 3.5 or change the version of any LLM, and we use this LLM in production, it means we're gonna have to either change the solutions if GPT 3.5 doesn't exist anymore, or modify the prompt again and again and again, just to track the model versions. So it's very cumbersome. And for these reasons, we decided to go with an open source LLM. And this is what we're going to talk about, is after everything, we're gonna finally fine-tune our own LLM on our data. So first, with fine-tuning an LLM, we need data or training data set. So I collected 6,000 lists of ingredients from the database, tried to remove I didn't try. I removed all the duplicates within the same data set, but also with the benchmark to prevent any data leakage. I reviewed manually 2,000 lists of ingredients using the Argila tool. Oh yeah, and reviewed because thanks to the benchmark we developed just before, we know that GPT 3.5 is the best model. So why not using GPT 3.5 to generate the corrections, and then use Argila to review these corrections and improve the data set. So this is what we did, and it worked super nicely. Perfect. And yeah, we're gonna come to that later. And also the data set, and it's super important for any step during the training stage. The dataset is versioned and hosted on Hugging Face. So Hugging Face, as you may know, is a platform to host models and datasets. But using the Python SDK could be actually super useful to track dataset versions during the training and during the experimentations. And by using the commits, we can track with a v1.1, for instance, we can track the version of the datasets, which is super handy when you experiment a lot. And yeah, I'm gonna show you that in the next slide. Additional note, we used GPT 3.5 Turbo to generate corrections, but also we use the guideline to prompt or instruct the GPT 3.5 to get the best corrections based on the guideline. So this is why the guideline is so important. It guides literally every step during this project, and we use it for the prompts. Now about the training pipeline. So before entering the pipeline, you may have tried or experimented with LLMs, and you may have seen that this is hard. This is hard for two reasons. The first one is these models are super large, but if they are super large, you need large resources. Usually people use Google Colab, but Google Colab is quite limited. First, you are limited to a notebook, and second, you're limited by the credits you have. Okay, you can pay for the credits, but maybe you need a larger resource to train your model for 3 hours and let your training perform during these 3 hours. And Google Colab doesn't allow you to do that, or at least at my knowledge. Second of all is because they are large, it's super difficult to manipulate them. So we need to find a way to manipulate them in an automatic way. And third thing is during the training, you have a lot of metadata, parameters, URLs where the data are, the version of the data sets, and so on. So we need to use the right tools to train our models in a reproducible and consistent way. So for these reasons, we decided to go with Comet and Metaflow. Comet to track the experimentations, but also all the metadata, and Metaflow, which is an orchestrator designed for machine learning development. It was developed by Netflix and open source by Netflix. And in my opinion, Metaflow is amazing, and I will explain why. But for this LLM training, any LLM training, it's super handy, and you will understand why. So the training pipeline, the first step of the training pipeline is to load all the parameters which are stored in the config file, so YAML file, and validate them. So they are validated with Python pick. And like that, you have one config file, and you change any parameter, and you iterate over it. Then, using Metaflow, we orchestrate everything. And for the training step, we load the dataset, the right version from Hugging Face platform. We train the model using TRL, which is a library now in the Hugging Face ecosystem, which makes the training of LLMs, to be honest, super easy. So training is actually not the hardest part at all, this step. And then we save the model artifact at the end of the training in S3. And we track the model artifacts by the training ID. As you can see, this step is handled by SageMaker. So why it's SageMaker? So first of all, with Metaflow, you have the possibility to externalize the resources during your steps, which is super handy. Like you can use AWS Batch Job, open an instance on AWS Batch Job containing a large GPUs, run your training, and then when the training is done, the instance is turned off and you don't pay anymore. So it's super, like you save a lot of money. But we decided to go with SageMaker because SageMaker comes with a lot of features. And instead of dockerizing your training script yourself, SageMaker does everything for you, plus additional features. I can talk a lot about SageMaker, but I love SageMaker training jobs. For that, they are probably the best, and especially for training LLMs, I can open or run very large GPU instances like I don't know, G5 or even G6 or whatever, and I just pay for the training. So it became super handy. Yes. So once the training is done, the model artifact is stored in S3. We're gonna retrieve this model artifact, and we're gonna evaluate the model on the custom benchmark we created long time before. But using the vanilla inference from Hugging Face, like evaluating the LLM, let's say 7 billion parameter LLM, it will take like 20 minutes to run on 320. But by using VLLM during the evaluation step, it can down to 20 seconds. So VLLM is an amazing tool for that. It accelerates. It's a serving library that serves your large language models in a very efficient way. And we're going to talk more about it later, but it's super handy. Then the predictions are stored in a S3 bucket with the same run ID. So you have the same run ID for the model artifact and evaluation prediction. And the next step in the Metaflow pipeline is a human in the loop evaluation, because what we have is metrics like precision recall, but it's still good to have a kind of a vibe check over how well the model performed, because the evaluation algorithm is not perfect. It makes sometimes in some very niche use case, it made some mistakes. So we need to have an overview and a visual. So for that, we use Avila, which is an annotation tool, but we use it just to visualize the results. And with this pipeline, we managed to do 200 experimentation, sometimes in parallel. Like you launch your experimentation, SageMaker open an instance, and then you run another one with another model or other parameters, and SageMaker open another instance, and everything is tracked, and so you can perform like a lot of experimentations almost at the same time. So it's super handy. In additional notes, why using an orchestrator like Metaflow or prefer to Airflow instead of just writing everything in one script or even using a Jupyter Notebook, because Jupyter Notebooks are super handy for that. The reasons is for debugging. Let's say my training pipeline goes well. I spent 3 hours training a large model, and it cost me, I don't know, $4 to train the model. And then I perform the evaluation, and it bugs. And if I had one script to do everything, I lose all my, let's say, URLs and metadata, and so I need to do that manually. And it happened to me that when I tried to perform that manually, I deleted some model artifacts just because S3 you can copy and delete model artifacts if you use the same URL. So using scripts or even Jupyter Notebooks, you can make mistakes. With Metaflow, the good thing is when, let's say, a step fails, what you can do is that you can resume the same training pipeline, because every training pipeline has the same run ID, has one run ID, and you can resume the training based on the last successful step. So like that, it makes any step super easy to debug, and that's why you have so many steps for the ease of debugability. During this experimentations phase, I tried various models. First, I wanted to start with very small models, like the basic T5 family. So T5 from Google in 2020, MT5, which is T5 but for multi-language, Flan T5, which is also T5 but with instruction fine-tuning, a bit like what we have nowadays. But actually, using a T5 family wasn't working at all. So I just increased the size of the models, and I use Fish3 Mini 4K from Microsoft, Llama 3.y 8 billion, Mistral 7B base V3, and also Mistral instruction. So I tried different base instruction, try to put an instruction and fine-tune everything with the instructions. So a lot of experimentation, but everything was managed by this training pipeline. Yeah, I think it's good for that. And the results, we got a model after 200 iterations. We got a model finally that performs better than any other LLM models on our benchmark. The best model was actually the Mistral 7B based VO3, and as you can see, it's only 7 billion. So first, we have a model and is way smaller than any kind of LLM that you can call via API. The second thing is we own the model. The model is now hosted on Hugging Face, the OpenFluxFacts Hugging Face repository. Anybody can use it because everything is open source, but especially we have the model, it will never change, and even if 1 year, it will still predict the same, it will still provide the same predictions that I used to do on the same benchmark even after 1 year. So we own the model, and it's super nice. Also, because we own the model, we can deploy it anywhere and how we want. And for optimizing performance, latency, or even cost, I will show you, is super handy. Quick test. If we run the model on the 50 sample of 5,000 products extracted from the OpenFluxFacts database, and we track the number of recognized and unrecognized ingredients, we witnessed an improvement of 11% of recognized ingredients on this sample. Out of a database of 3.5 million products, it's definitely a success, at least for this model. And yeah, we have total ownership. So now we have the model. We need to deploy it somewhere. So as you may know, in machine learning, we have different ways of deploying a model. We can either deploy it in real time, which means we open a GPU instance and it runs 24/7, and we pay for the time it runs. But for our use case, it can work. But we already have 3.5 million products, and maybe 200, maybe 20% of these products that contains spell check errors. So we need to fix this database first. And the best way to fix this database is to use the batch deployment. So this is the batch deployment architecture we decided to go with, and let me walk you through. So here what you can see is the Robotoff, which is a machine learning microservice hosted by OpenStack. So everything related to machine learning is developed in this microservice, developed and deployed. And before running the batch job, we have an image containing the model, or actually we load the model, containing the model and the library VLLM, which will be super useful to accelerate the inference by batch. You will see that it's pretty amazing. Okay, so how does it work? So in the Robotoff microservice, I created two endpoints via the API. One is batch launch. So you're gonna launch the batch I don't know, algorithm in the API. And what does it do? It will fetch data from the OpenStack database using DuckDB. I can talk a lot about DuckDB, but let's keep it simple. It's a data transformation and processing tool, which is super fast and super light. I love it. So the data will be fetched from the OpenStack database, pre-processed and stored in the GCP bucket. Then as pre-processed. Then the batch job in the same call, HTTP call, the batch job in GCP will be launched. An NVIDIA L4 GPU will be launched as well, and it will pull the image from the image registry containing the model and the LLM and process by batch the sub-batch the preprocessed data parquet, and then store the results in a process data parquet in the same Google bucket, and then it will call using an HTTP request the API with the notification to start the next step. And the next step is exporting this process data to the Robotoff database containing all the predictions, and these predictions will then be integrating into the front end for user validations or correction during the edition of a product. So a user will use the applications or the web application, and he will modify the product, and then we're gonna suggest him the predictions of the LLM, and it will have the final decision. It will take the final decision whether to validate or correct or invalidate maybe the prediction. So like that, we leave to the users the let's say the complete control over the quality of the database, and the LLM is just here to facilitate the process. Talking about performance now, processing 100K list of ingredients only costs using GPU L4 $2. And by comparison, if you try to do the same with GPT-4o, it will cost $180. So in terms of cost, even if we have our own LLM using the right infrastructure, made us the best cost optimization or cost performance. Also in terms of performance, using the L4, and the LLM especially, processing 100K lasts 2 to 3 hours, which is super fast. And that's pretty much it for the batch deployment. Currently the integration of the LLM prediction is still a work in progress. So a front-end developer has been hired to implement all the LLM predictions into front-end components, and we hope that in 2025 the complete feature will be up and running. As a conclusion for this presentation, when you have this kind of project, like anyone would love to go directly into training or using an API, LLM, extra. But you need to start first with the problem you're facing, and especially how can you evaluate it? Because if you can evaluate it, the problem is half solved. And yeah, for me, but to be honest, it's you need to evaluate your solutions, like that you can compare and evaluate the performance and say to your stakeholders, I deployed that and look at the results, and it performs way better. And so using open source LLM was the best choice. Should you use an external LLM in your NLP problem? So everybody nowadays is using LLM for literally everything, but there are still NLP problems. NLP problems, I'm talking about sequence like we just solved, or text classifications, or name entity recognition. And right now, the LLMs can do the job. But should you use an external LLM for this? So my opinion on this is using an external LLM is good for building a POC or for validate the feature. It takes time to build machine learning features, like fine-tuning your LLM, integrating it, deploying it. It takes a lot of time. So at least using an external LLM for building a POC is the go-to. You need to do that for the POC. Like whatever. Also, the external LLM is super useful for generating synthetic data that then will be used to train smaller and maybe open source models. Actually, no, open source models. And as we did in this project. For me, the external LLMs are super useful for these reasons, and I'm talking as an NLP machine learning engineer. Generate synthetic data. The last thing is, if you use an external LLM directly into your features, let's say, are you willing to send bad predictions to your users right away? Like, do you think like your users will trust you if you send very bad prediction because you just prompted an API LLM from, I don't know, OpenAI? And this is a very important question today. It's like, okay, you have the performance, but oh no, you can create features very fast with LLMs or external LLMs, but do you really want to use your users as ships to just test your features? So it's a very important point. As you may see, as you have seen, the training stage is actually the list of your problem. You need to manage everything around, like the training pipeline, storing the data, creating the evaluation benchmark, etc. So training was actually maybe not the easiest, but one of the easiest part of this project. And it will always be in machine learning projects. In talking about machine learning projects, nowadays, and as a freelancer, I see it a lot with the clients I work with, developing an ML feature, or let's call it an AI feature, looks super fast using an LLM or an external LLM. But whenever you want to implement the data and to fine-tune and deploy your own solutions, it takes time. It's a matter of months, if not a year, like between 4 months, 6 months to 1 year, to be honest. So it's a long process, and sadly, this is a data problem. It's not a model problem. Data is hard. And finally, if you own your LLM, you own the infrastructure, and you depend on nobody else, and you can optimize everything with the proper knowledge by using the right deployment strategy, and you can optimize everything from the performances to the cost. So yeah, it's very much for me. Thank you for your attention, and I'm open to answer your questions.
Well, let's thank Jeremy for a wonderful presentation. I learned a lot and I got a ton of questions, but let's open it up for Q&A. So if you guys have questions, drop it in the chat or feel free to raise your hand.
Hi, really thanks for the session. Shabi, I'm a good, active follower for your YouTube channel. Thanks for that. Thanks for arranging this session as well. Yeah, my question to the presenter is, may I know the model size and type of instance we used, for inference, how many concurrent requests it can handle in parallel. I like to know about that.
It depends. So you're talking about VLLM, right?
Whatever model we finally deployed in production, right? So how big is that? How much RAM it required to perform inference? And let's say if I'm sharing this model with the API wrapper, how many concurrent requests it can handle, how many users can interact with our model through API, how many what could be the system power, how we are dealing that.
So I will answer in the very famous way. It depends. So first, we haven't chosen we didn't choose the real-time inference. So we don't have concurrent users. We have a batch job, and we open an instance, and we run the job on it. And when the job is done, we have the process data. So for this, we don't have concurrent users, so we don't have this issue. But if you
but from your experience, if you can share your insights, let's say I'm having a model with it can occupy 7 GB RAM or 50% of my CPU, in one core. How many inference I can make in parallel in that case?
To be honest, I'm not sure either, because I never use VLLM to deploy a real-time system. And it depends also about of course, VLLM, but also the precision of your model. If you are in 16 bytes, no, sorry, 16 bits, or 8 bits, or 4 bits, and the lower, the faster. So it depends a lot, and you need to test. To be honest, I haven't tested it yet. I would like to test it with Locust to test the load, but I cannot answer precise answer.
Okay, because most of the times, in companies, the model development, packaging the stuffs and all, we have good guidelines, we can do that by following steps, everything. But what happening is, in the end of the day, the company asks, what would be the cost? Let's say if I'm having, this much concurrent user, how much infra required, and what kind, what would be the cost, monthly cost for servers and all. To predict that, we don't have such a system. I mean, from my knowledge, I don't have. So I'd like to know that from you. Yeah.
So yeah, actually, I made a bit of calculations about that. So right now, the NVIDIA L4 works super well, high memory, and very cost efficient, and VLLM works super well as well, and is optimized for page attention and processing different requests at the same time. So VLLM is definitely the go-to. You can also try the TGI from Hugging Face, and it's made for concurrent requests for LLMs. And let's say you want to you have Kubernetes, and you want to serve VLLM that comes with a Docker image, by the way. You use NVIDIA L4, and it will cost you $600 a month to have the instance running 24/7. And I use L4 with VLLM to run batch jobs with the Mistral 7B, and it works super nice. I'm pretty sure that with VLLM, the way it's architecture, it can handle several requests at the same time. So consider a cost of $600 minimum. But you already have very good performance, because the L4, like I said, is 24 gigabytes of VRAM, and if I remember well, actually we can do quick math, but let's say you have Mistral 7B in 8 bits, so it would take you 16 gigabytes, but as a vanilla inference. But with VLLM, you don't use the full memory. You use like page attention, and it's super optimized. So with $600 a month on Kubernetes, you already have your real time. I need to try that myself and load it, but load it with users.
Sure. Thank you so much for your.
Yeah, great question. This VLLM seems like the real game changer for self-deployment folks. Let's see. We got a couple questions in the chat here. So DJ asked how to keep ourselves AI proof. There's too much AI fear on social media these days. Perhaps you and I contribute to that with our LinkedIn posts, Jeremy.
I can start and then sure you can continue. So AI proofed is very funny because I'm super AI proofed, and the proof of that is I haven't touched AI for maybe 4 months, just because there's so many informations and so much noise that I don't have time for that. And to be honest, I just want to do real stuff and MLOps stuff and deployment and solving real issues. So the best way to protect yourself from that is to take a break, learn something new, something else related to machine learning. I'm learning personally Kubernetes, and when the noise will settle down, all the hype with AI will settle down, I will come back. I will have exactly the same knowledge in machine learning, but to be honest, it never changed that much. Like we still use transformers, and we just have a couple of new libraries, but behind the scene, we still use Hugging Face. So nothing changed since 2021 or 2020. So you're still good, and you have a new knowledge, and you know how to deploy models on Kubernetes or Cloud Run. So yeah, take a break and just come back in 6 months.
I have one answer that aligns with yours, but I guess I have two things. Like, number one, focus on solving problems, because that's never gonna go bad. That's never gonna go out of fashion. People will always pay you to solve their problems. And two, kind of to what Jeremy is saying, like, learn something new, but something that's not like brand new, like, you know, something that just got released last week, but ideally something that's much older. So ideally, the older, the better. So maybe you can go read like old philosophy books, or you can read old math papers or physics papers, or, you know, maybe even Kubernetes or something like that. The older is better, because if it was like if something came out 10 years ago and it's still around and people are actively using it, it's probably going to be around in like 10 years. So that's just like a heuristic.
Exactly. The fundamentals.
Yes.
In software, because machine learning is a part of software, and fundamentals even in deep learning and how transformers access through rocks and stuff like that. So fundamentals.
Another question from Florian. He's interested in why you think GPT 3.5 was the best of the different LLMs you used.
So it's there's maybe a bias. I haven't mentioned it, but the benchmark was in I didn't even heard about it. The benchmark was reviewed, but it was first synthetically generated using the prompt with GPT 3.5 Turbo. So GPT 3.5 Turbo made all the corrections, and then the corrections were reviewed using Argila. So we spent a lot of time review the benchmark, and actually the benchmark is good, but it was generated with GPT 3.5. So I think there is a bias, because why GPT 3.5 Turbo works well, but at the end we have the human review, we see it, we like the benchmark, we validate the benchmark, so let's be. And if GPT 3.5 generates what we like, so we're gonna use it to generate the training data set. So that's why the bias.
Question related to the LLM benchmark. The sampling parameters of LLMs affect the prediction. Was the LLM benchmark evaluated only on a single combination of all sampling parameters, like temperature, top P, top K, benchmark, value of different sampling? Okay, so I guess the question is how the tokens were like sampled from the LLMs. Like, did you experiment with different configurations of that, like different temperature values, you know, things like that?
To be honest, not that much. The prompt, I didn't optimize the prompt that much. Like, okay. I didn't use tools to optimize the prompt. The temperature is set at 0. experiment sheet, and then a lot of iteration on the prompt for some LLMs. The prompt was a bit tweaked depending of the LLM, because for instance, Claude Sonnet 3.5, is it? Yeah, probably. I'm a bit lost. Is a bit tricky because it tries to answer you in a very nice way and give you corrected it, that's why, because, and super awful, so you need to adapt it a bit. But I haven't done a proper experimentation for the LLMs. One of the reasons is we knew that using an LLM or an external LLM will not be the final solutions in production, just because of the ownership, and also because OpenShiftFax is an open source project, and using a non-open source model would be like contradictory. So yeah.
Oh, yeah, that's super interesting. Got a couple more questions. Arvind asked, what challenges did you face while operationalizing the model into production? Tough word.
Honest answer, the hardest part was having all the administration access and the how do you call it, the policies from GCP. It was the hardest because actually I need this. I need to wait 2 days to have the access or the availability. I don't know the whatever. And so this was hard, but no. Also, it wasn't hard. It just took a couple of days. But what kind of configurations is the best for VLLM on L4? For instance, L4 compared to other GPUs, I tried different GPUs as well. I think I tried A10, and L4 is actually super performant with 8 bits. But A10, if I remember well, is not performant at all with 8 bits. I also tried Llama CCP on on CPU, just try the real time, but also some batch processing. And all this experimentation phase of finding the best configuration was a bit tricky, to be honest. And at the end of the day, it was VLLM, 8 bits, and GPU L4. But you need to benchmark a bit about, okay, what kind of precision do I need and how does it impact the performance? That's why also you need the evaluation benchmark, because if you quantize it, you need to see how bad the performance are. So this was the main challenge.
So number one pain was setting up permissions on GCP.
Permissions.
Second pain was all the different experiments, just because of the sheer volume of different combinations.
Yeah.
Oh, it looks like we got a ton of questions. Okay, let's try to get through all of these. He's asking about the precision of the LLMs for the final one you deployed, like the fine-tuned Mistral, or the Mistral model that you used. Did you do FP32, FP16, or something else for the inference?
Bfloat 8 bits, and I got the best performance over it. Is it a question? I don't think this is a question.
Yeah, that was the question, and then like, what was your logic, like the reasoning behind choosing BrainFloat 8? Did you explore any other options?
I tried Float 16. I think it was I tried Float 16, but I got the best performance with 8 bits, to be honest. So that was just in terms of performance on a very simple benchmark I did manually.
That's interesting. So like the prediction performance was best, or like the latency, like performance in terms of latency?
The latency.
Okay, got it.
Yeah.
Let's see. Yeah, sorry.
Because NVIDIA L4 is, I didn't know about it before, but NVIDIA L4 is quite optimized for Bfloat 8 bits.
I would like to know how the baseline performance was chosen or achieved in the fine-tuning step. Maybe that's referring to the LLMs you experimented with?
Yeah, the baseline was a GPT 3.5. So we were like, we have a model that we can deploy in production, which is the GPT 3.5 Turbo. This is the baseline, we need to beat it. And actually, even if we don't beat it, it's maybe still fine, but we need like a similar performance at least, because even if we don't build it, we have the ownership over the model. So this is good. No, otherwise, no. I don't think there was a baseline. No, there was no baseline. If I remember of baseline, I picked. I will tell you. But the GPT 2005 performance was the baseline.
And then we got another question that just came in. Low size versus big size model. How do I choose? Like, which one do I choose? Low size seems to give faster responses.
But to be honest, I'm like, I don't like large language models. I think it's too much. I love sklearn because it's you can run it on CPU. It takes no time. It's super easy to deploy. And now you have the big, large language models. You need GPUs. It's costly. You need to integrate everything. It's like awful. So I started with small language models, which is diff5, which is the encoder decoder from the transformer architecture. And you know what? It was bad. It was a bad idea because the performance based on the evaluation algorithm were super bad, and I couldn't figure out if it was super bad because of the data, because of the hyperparameters, or just because of the model. And as soon as I switched to Mistral 7B, the results were finally decent. And so small, large, it depends. But to be honest, if I had to do the project again, I would start with large language models, which is super funny because usually people say the opposite in machine learning, start with a rule base and then use that. But if you do machine learning from the beginning, start with large language, especially in natural language processing. Start with large language models, okay, make it work. It's easy, right? You need a GPU L4, or you go on Lightning Studio or Colab, but Lightning Studio, I don't use Colab. And you make it work, you check the performance, you know you can deploy it for $600 a month, so it's good. And then you go down, because like starting from the bottom, it's like, does it work because I messed up, or does it, it's not working. Is it because I messed up somewhere, or is it because it's just a model? And I lost maybe a month on T5 family, and I'm glad I dropped them for Mistral and the other LLMs.
No, that's super insightful. Start big, get the performance first, and then start working your way down for smaller and smaller models.
It's only for machine learning and NLP and LLM, and because it's like there is too many factors, and you know whether your error is from.
All right, awesome. Well, let's thank Jeremy once again for a wonderful presentation and great insights during the Q&A. If you guys had questions that we didn't get to, feel free to reach out to Jeremy on LinkedIn. I'm sure he'll be happy to answer your question. And then thank you to everyone who joined in the audience and all the great questions. So the recording will be uploaded to YouTube tomorrow morning. And if you registered, I will email you a link to the recording so you can check it out. Next week, I'll be giving a presentation. So if you guys want to check that out, that's going to be on content creation. But yeah, so you'll also be able to see that on our events calendar. And with that, thanks again for joining, and we'll see you in the next one.